Hey everyone, in this video we're going to go over section 4.5, Summary of Curve Sketching. This section is largely going to kind of summarize a lot of concepts we've talked about up until this point, and some chapter 1 stuff we skipped over. So really this entire section boils down to kind of like a 7-part process for us to graph functions. So just diving into it, the first thing that we want to consider, and the book letters them, I'm going to number them, we want to consider the domain of a function. The second thing we want to consider are the intercepts. And by intercepts we mean both the x-intercept, or x-intercepts, there can be more than one, and the y-intercept. And that was supposed to be a hyphen, not a comma. Sorry about that. Now it looks like a semicolon. 3, we want to talk about symmetry. Now symmetry was something that was in chapter 1. I know that it gets talked about a lot in college algebra, it gets talked about in trigonometry, so I'm going to refresh here. By symmetry, we know a function is even, or it has y-axis symmetry. Axis symmetry. If f of x is equal to f of negative x. Think of something like y is equal to x squared is even. So for odd, we have f of negative x being equal to negative f of x. This is another way of thinking of, instead of y-axis symmetry, this is symmetric about the origin. Think of something like y is equal to x cubed or y is equal to x. Any of these points where if you have the point, say, we'll call that 1, 2, you have the point -1, -2 also on the graph. And then finally, we have a periodic. The rigorous definition of a periodic function is any function that satisfies this equation, and we would call P the period. Think of your sines, your cosine, your tangents, really any of your trig. Any of your trig functions would fall under periodic. The first thing we want to consider are asymptotes. And we'll use our limits. Remember, we have vertical asymptotes when our denominator goes to 0, and we also want to take limits going to infinity, positive and negative infinity. We want to consider intervals of increase and decrease. We want to find local maximum and local minimums. And the last thing we want to do is we want to discuss, or we want to explore, concavity and inflection points. So this is our big 7-step process. I don't know why they broke this first derivative stuff into 2 and they left the second derivative stuff as 1. But from our domain, our intercepts, our symmetry, and our asymptotes, all of this information we'll get from just f of x. And asymptotes from f of x. Intervals of increase and decrease as well as local max and min. This information comes from f prime of x. And concavity and inflection points comes from the second derivative, f double prime of x. So this is our summary of curve sketching. This is kind of everything we should know up until this point. If you guys haven't seen symmetry for a while, we're going to check it every time. It definitely helps you in graphing these things. But it won't be, what's a good way of saying this? Don't be stressed out if you haven't done a lot of stuff with symmetry lately. But aside from that, we're working with our original function, we're working with our derivative, we're working with our second derivative. So let's use all this kind of as our roadmap to graph a function. Perfect, so let's use these guidelines to sketch a curve. Let's sketch y is equal to 2x squared all over x squared minus 1. Minus 1. So the first thing we need is the domain. Well, we're not taking any square roots, so there's nowhere to take the square root of negative number. We're not taking any logs anywhere, so the only real rule that we can break is dividing by 0. Looking to the denominator, we see that x cannot be equal to plus or minus 1. For intercepts, for our x-intercept, that tells us take y and set it equal to 0. We get 0 is equal to 2x squared over x squared minus 1. Multiply both sides by x squared minus 1. 0 is equal to 2x squared, and we get x is equal to 0, which has a multiplicity of 2, which tells us that we are going to touch the axes, or touch the x-axis at the point 0, 0. For our y-intercept, that's where we take x and set it equal to 0. That means y is going to be equal to 2 times 0 squared all over 0 squared minus 1. 2 times 0 squared is 0, and we get y is equal to 0. Or we have the y-intercept being at the point 0, 0. Perfect. Let's move on to symmetry. So for symmetry, we want to test even. So hopefully you guys are okay with the point. If we have this function y being equal to 2x squared over x squared minus 1, we can just rename this function f of x. Just changing its name. The reason why is because symmetry uses this notation. It's a little bit easier to switch to this notation. Regardless of which test we're testing, we need to figure out what f of negative x is. F of negative x is equal to 2 times a negative x squared all over a negative x squared minus 1, which negative x squared is the same as a positive x squared. And we see that f of negative x is the same as f of positive x. This tells us that f of x is even. And then we can test odd. To test odd, we need to figure out what negative f of x is, and that's a negative 2x squared all over x squared minus 1, which is different than f of negative x. So this tells us f of x is not odd. Finally, f of x contains no periodic functions, such as trig functions. So, f of x is not periodic. Perfect. So, we know it's even, it's not odd, and it's not periodic. Now we move on to asymptotes. Well, first off, we want to talk about vertical and horizontal asymptotes. For our horizontal asymptotes, we want to take the limit as x goes out to infinity of 2x squared over x squared minus 1, which, as x gets really large, our numerator tends to infinity, and our denominator also tends to infinity. So, we can use L'Hopital's rule. We know that the limit, as x goes off to positive infinity, of 2x squared over x squared minus 1 is equal, by L'Hopital's rule, the limit, as x goes off to infinity, of 4x divided by 2x. These x's will cancel each other out, and this is equal to the limit, as x goes off to infinity, of 4 divided by 2 is 2, which just equals 2. This is where evenness can come into play, because whatever happens on one side of the y-axis, like a function limiting towards 2, has to happen going into the other direction. So just by knowing that we're even, and I have lost my page, by knowing that we're even, we also know that the limit, as x goes off to negative infinity, of 2x squared over x squared minus 1 is also going to be equal to 2. If you guys didn't notice, if you guys didn't say or notice that, hey, this function is even, therefore we can get this result, if you were to go through these steps, you would still get to the same result. There's nothing that you have to get from symmetry that you won't get somewhere else. It's just you get information that might help you later on from symmetry. So we know we have these horizontal asymptotes along the line y is equal to 2. I'm going to put that in a box because I'm probably going to lose it later. And now we need our vertical asymptotes. Well, we know we have a vertical asymptote where denominator goes to 0. And so we know that that happens when x is equal to 1 or x is equal to negative 1. The thing is, we want to figure out if the function tends towards positive infinity or negative infinity. These limits might not exist. They could go in opposite directions. So that means we want to go from both sides going to positive 1 and both sides going to negative 1. So we're also, because it's going to be easier to think about, I'm going to rewrite our equation. Y is equal to 2x squared all over x plus 1 times x minus 1. So if we want the limit as x goes to negative 1 from the left of 2x squared over x plus 1 times x minus 1, well, if we're coming up to negative 1 from the left, all of our numbers are going to be slightly smaller than negative 1. They're going to be to the left of it. They're going to be like negative 1.1 or negative 1.01. Regardless, whatever number x is taking at the time, 2x squared, or 2 times x squared is going to be a positive number. That's going to be divided by, well, if we have something smaller than negative 1 and we're always smaller than negative 1, then x plus 1 is always a negative number, and our x minus 1 is always going to be a negative number. So we know we have to go to positive or negative infinity because the denominator goes to 0. We have positive divided by negative times negative, which is a positive, so we know we're going to go out to positive infinity. If we take the limit as x goes to negative 1 from the right of 2x squared over x plus 1 x minus 1, well, once again, whatever value of x is, 2x squared is going to be positive, and that's going to be divided by, so a number slightly to the right. This is going to be something like 0.9 or 0.99 or 0.9999, negative 0.9, negative 0.9, or negative 0.999. So x plus 1 is always going to be a positive number. Now x minus 1 is going to be a negative number. So we've got to figure out if we're going to positive or negative infinity. Positive divided by the product of positive and negative is negative, and we'll go to negative infinity. That takes care of negative 1. Now we have to take the limit as x goes off to positive 1 from the left of 2x squared all over x plus 1, x minus 1. Numerator is going to be positive divided by, this is like a positive 0.9 and a positive 0.99, so we're going to get a positive number and a negative number, and that'll kick us out to a negative infinity. And finally the limit, as x goes off to 1 from the right, of 2x squared over x plus 1, x minus 1. Numerator is positive. Whatever value of x is, x plus 1 is positive. And x is always slightly bigger than 1, so x minus 1 is always a positive number. And we get a positive infinity. So, as we approach negative 1 from the left, we go to positive infinity. As we approach negative 1 from the right, we go to negative infinity. As we approach positive 1 from the left, we go to negative infinity. And as we approach positive 1 from the right, we go to positive infinity. Now we need intervals of increase and decrease. In order to get our intervals of increase and decrease, we need our first derivative. So, this will be for 5. If f of x is equal to 2x squared over x squared minus 1, then f prime of x, by the quotient rule, is equal to low times the derivative of the top minus the top times the derivative of the bottom, all divided by the denominator squared. We can simplify some things. 4x times x squared gives us a 4x cubed minus a 4x, and we'll minus a 4x cubed all over an x squared minus 1, quantities squared. These will cancel, and we're left with f prime of x being equal to a negative 4x divided by the quantity of x squared minus 1 quantity squared. We're looking for intervals of increase and decrease. Well, if you look, regardless of the value of x, our denominator is always positive. Regardless, we're going to square this thing. And so the sign of f prime is going to be dictated by the sign of the numerator. We see that f prime of x is negative when x is positive. And f prime of x is positive when x is negative. So that tells us that we are going to decrease. We are decreasing on or over 0 to positive infinity, and we are increasing on negative infinity off to 0. Perfect. So now we need to figure out our local max and our local mins. So for our local max and local mins, we want to consider where the derivative doesn't exist and where the derivative is equal to 0. So right here, our derivative is going to equal to 0 when x is equal to 0. F prime of 0 is equal to 0. It's the only value of x that will make our derivative equal to 0. So we have one critical number. X is equal to 0. By the first derivative test, we know that this is going to be x equals 0 is a local max. So what is that first derivative test? That first derivative test, and I'll draw you the two pictures for it. Well, there's really three. I wanted to be technical, there's 4. That one's kind of like 2. What the first derivative test says, if your derivative goes from positive to negative at a point, you had a max. If your derivative goes from negative to positive at a point, you had a min. And if your derivative either stays positive or stays negative, you know that you have neither max nor min. No max or min. Since our derivative is going to go from negative to positive at that point, is going to go from, since our derivative is going to change signs when x is equal to 0, and we're going to go from a positive derivative to a negative derivative, we know we're going to have a max when x is equal to 0. You also could throw it into your second derivative and use the second derivative test. By the second derivative test, this function is going to be concave down at that point. Or you can use the first derivative test. So that is real quick. In this function, it was fairly easy. It was straightforward to be able to look at the numerator and go, oh, whenever x changes from 0, anything above 0 to anything less than 0, our sign is going to change. Sometimes, I personally think it's much easier to find your critical numbers before you find your intervals of increase or decrease. You don't have to do every step in every single order. Especially when you get to these two sorts of derivatives, you're really doing 5 and 6 almost at the same time. And in fact, you're doing the same stuff for 5 and 6 as you do in 7. You're just working with the second derivative instead of the first. So I don't want you to get this summary etched in stone and think that you have to do it this way every time. What we're really doing is getting information from our function, from our first derivative, and our second derivative. You guys are supposed to know, you guys are supposed to be learning, you guys hopefully by the end of the semester will know what information you can get from functions, their first derivative, and their second derivative. So this is really just trying to get you guys to kind of localize all of these thoughts in your brain and put them all together. So don't be afraid if you do 6 before 5. Don't be afraid if you do 5 before 6. This is largely a choose your own adventure book, so you can do the steps in some logical way, something that makes sense to you, as long as you don't break the rules of math. Final step is we need to find concavity and inflection points. I think I've ran out of space. Almost ran out of paper. So for 7, so in order to find concavity and inflection points, we need that second derivative. So I'm going to start with the first derivative. F prime of x is equal to a negative 4x divided by x squared minus 1 quantity squared. And now we'll figure out what the second derivative is. So by the quotient rule, f prime, and we've got a chain rule floating around, going kind of quickly, f double prime of x is equal to low x squared minus 1 squared times the derivative of the top, which is a negative 4, minus the top, which is a negative 4x, times the derivative of the bottom, which by the chain rule is 2 times x squared minus 1 times the derivative of the inside, which is 2x, all divided by the denominator squared. X squared minus 1 squared squared. I always forget to square the denominator. Just be careful. I to this day forget to square the denominator. So now let's go through and let's simplify this thing. Really, I'm just going to try and rewrite at this stage. Bring that negative 4 out front. X squared minus 1 quantity squared is x to the 4th minus 2x squared plus 1. Oh, this minus sign and that minus sign are going to cancel. We're going to get a plus 4, 8, 16x squared times x squared minus 1 all over our denominator squared. X squared minus 1 quantity to the 4th. Let's keep on going. This will be equal to a negative 4x to the 4th plus an 8x squared minus 4 plus 16x to the 4th minus 16x squared, all divided by x squared minus 1 to the 4th, which now we can gather some like terms. This is, we have 16 take away 4 gives us 12x to the 4th. We will have a negative 8x squared, and then from that we'll subtract 4. All this is going to be divided by x squared minus 1 to the 4th. And if you look, our numerator, we're going to try and factor this thing. My hint was that we have something like an x squared squared, something like an x squared to the 1, and an x squared to the none. So the first thing I'm going to do is I'm going to pull out a positive 4 from that numerator. 4 times 3x squared minus 2x minus 1, all divided by x squared minus 1 to the 4th. At this point, I'm going to factor by grouping. I would definitely, you guys are kind of on the honor system to do this. You don't have to factor by grouping. I'm not going to lie to you and say that the internet isn't full of factoring calculators. I will say that factoring comes back in Calc 2 for those of you who are planning on taking Calc 2 next semester. I definitely would not forget how to factor. It'll help you in the future. So we're looking for numbers that multiply to negative 3 but add to negative 2. That's got to be 4 times 3x squared minus 3x. I'm sorry, I should have an x to the 4th, and I should have a negative 2x squared, which means this should be an x to the 4th, which means this should be a minus 3x squared plus an x squared minus 1. All divided by x squared minus 1, all to the 4th. Factor by grouping, we're going to group these and these. This will turn into, the back of this page, this will turn into a 4 times, I can pull a 3x squared out, times, we'd be left with an x squared minus 1 plus an x squared minus 1, all divided by x squared minus 1 to the 4th. Perfect. I'm going to factor out this x squared minus 1, and that'll give us f double prime of x is equal to 4 times x squared minus 1 times 3x squared plus 1, all divided by x squared minus 1 to the 4th. This x squared minus 1 is going to cancel out with one of those, and we're left with f double prime of x being equal to 4 times 3x squared plus 1, all divided by the quantity of x squared minus 1 cubed. Perfect. So, this is just our second derivative. Now we can finally get on with figuring about concavity and inflection points. Our inflection points, that's when f double prime of x is equal to 0. Well, no matter what value of x you plug into this equation, your numerator will never equal 0. Whatever value of x you plug in, you're going to add 1 to it, then you're going to multiply it by 4. You're going to square it, then you're going to add 1, then you're going to multiply it by 4. You're always positive. So this never happens. So we have no inflection points. So now we want to figure out where we're concave up or concave down. So like I said, our numerator is always positive. Our numerator is always positive. So the only time that we're negative is when our denominator is negative. And our denominator is negative when x is outside of the range from -1 to 1. So said differently, we get that f double prime of x is going to be bigger than 0 when x is in, we want -infinity to -1, union with 1 out to infinity. And f double prime of x is going to be less than 0 when x is in -1 to 1. So for any of those values, let's say a half that's in here. A half squared is a fourth, take away 1 is -3/4, cubed is -27 on 64. So there we go. You're free to do this more algebraically. You would want to figure out where that thing is bigger than 0 or less than 0 and go forward with it that way. You're also free to kind of point and say trends, like this is always positive, so because of that we know this. You don't have to do as much algebra as you did in an algebra class to get all the points needed for a calculus class. So this is everything we need to know about this function. Not everything we need to know. There's more stuff we could do. We could, for fun, we could plot a bunch of points. We've got a rule, and I'm lost. We have a handy-dandy rule that relates values of x and values of y. Let me find my paper and I'll be back. Surprise, they're all my papers. So let's combine all of this. I'm going to move the directions so I don't get lost again. And so now we're trying to take all this information that we have. I am going to draw a graph. So we know we're going to touch when we're going to touch the x-axis at the point 0, 0. We know we have that point. This is everything we know for 2, I should say. 2 is done. What is 1 good for? 1 lets you know where you should be graphing. Knowing the domain also helps you when you go back to 3, wherever I have it hidden. When you're talking about horizontal asymptotes, your domain also helps you there. So that's 2. Our horizontal asymptotes, and I want to make sure, we'll use evenness in a second, I won't throw that away. We know, we'll call this 2. And we also know we have these vertical asymptotes. At -1, and another one at +1. Don't need to write +1. Perfect. And we know that as x approaches -1 from the left, we go to positive infinity. So as we approach from the left, we're going up to positive infinity. And as we approach -1 from the right, we're going to negative infinity. As we approach 1 from the left, we're going to negative infinity. And as we approach 1 from the right, we're going to positive infinity. We also know that we're going to tend towards positive or negative infinity. Now there's a couple things before I just draw an arrow here or an arrow here. Let's talk about our concavity. Let us talk about concavity. We know that we're concave up from -1 to from negative infinity to -1 and from 1 to infinity. Concave up means we're always pointing up. What does that mean? That means, because we're always positive, we can't have anything that looks like this. Because at this point, once we stop increasing, there has to be a point over here where our concavity changes, even without all the wiggles, just focusing on one side. Convince yourself that if we overshoot our horizontal asymptote, there has to be some point where our concavity changes. So we can't overshoot our asymptote, so we're going to curve. And we're going to curve. Perfect. So we also know that we're concave down on this interval. So we're never going to wiggle up or down. We have to stay concave down. And we're even, so what happens on this side has to happen on this side. We're also concave down. Perfect. This is a sketch. This is my sketch of y is equal to 2x squared over x squared minus 1. It gives us a lot of important information. We've got our one critical point. Our x-intercepts, our y-intercept. We know about end behavior. We know about asymptotes. This gives us a good idea for what the curve is supposed to look like. All this really, like I said, is an exercise in getting you guys to really group all this information in one folder in your brain. Try and get you guys to see how functions and their derivatives relate to each other. So we'll do a couple more examples. Let me get set up. Alright, so let's sketch another one. Example 2. We're going to sketch y is equal to x squared divided by the square root of x plus 1. The first thing for our domain, well, x squared, x can be any number if we're going to square it, but we can't take the square root of negative number. So we need x to be bigger than or equal to, not equal to, just bigger than negative 1. Because we also can't divide by 0, so we have to exclude negative 1. For 2, for our intercepts, for our x-intercept, that means y is equal to 0, and we get 0 is equal to x squared over the square root of x plus 1. That can only happen when x is equal to 0. So we get the point 0, 0. Once again, 0 is a 0 of multiplicity 2. We're going to touch at 0, 0. Our y-intercept, well, if we're going to cross at 0, 0, 0 is going to be our y-intercept as well. Y-intercept tells us take x, set it equal to 0. Y is 0 squared divided by square root 0 plus 1. Equals 0, 0, 0 for our y-intercept as well. F of negative x is equal to x squared over the square root of negative x plus 1. F of x is equal to x squared over the square root of x plus 1. And negative f of x is equal to negative x squared over the square root of x plus 1. Since f of negative x is not the same as f of x, we know we're not even. Since f of negative x is not the same as negative f of x, we know we're not odd. And since we don't have any trigonometric functions popping up, we know that we're not periodic. So we have no symmetries. And this was 3. For 4, we need to go over asymptotes. So we want to take the limit as x goes off to infinity of x squared divided by the square root of x plus 1. We go off to an infinity divided by an infinity. So the limit as x goes off to infinity of x squared over the square root of x plus 1 is equal, by L'Hopital's rule, the limit as x goes off to infinity of 2x divided by 1/2 of x plus 1 to the negative 1/2 times the derivative of the inside, which is 1. This is equal to, by algebra, the limit as x goes off to infinity of 4x times the square root of x plus 1, now to the positive 1/2. Infinity times infinity is just an infinity, so this thing tends to a positive infinity. So we know that we do not have a horizontal asymptote. But let's check what happens as we run up, as we let x tend towards negative 1 from the right. Note that we can't approach negative 1 from the left because it's out of our domain. As we approach negative 1 from the right, we get x squared divided by the square root of x plus 1. Well, this value, whatever x squared is going to be positive, and this value is going to go to 0, but from a positive direction. So we're going to shoot up towards positive infinity. So we know we have a vertical asymptote along the line x is equal to negative 1. Intervals for increase and decrease. This derivative gets a little big. Let me get another piece of paper out. So, if f of x is equal to x squared over the square root of x plus 1, then f prime of x is equal to, by the quotient rule, we're going to get low. I'm going to go through x squared over x plus 1 to the 1/2. So, is going to be low. X plus 1 to the 1/2 times the derivative of the top minus the top times the derivative of the bottom. 1/2 of x plus 1, negative 1/2 times the derivative of the inside, which is still 1, all divided by the denominator squared. X plus 1 to the 1/2 squared, which I'm going to go through and I'm going to call this 2x times x plus 1 to the 1/2 minus x squared divided by 2 times x plus 1 to the 1/2, all divided by x plus 1. It's going to leave in parentheses. I don't want compound fractions, so I'm going to go through and multiply top and bottom of this fraction by 2x plus 1 to the 1/2, 2x plus 1 to the 1/2. These will cancel. Now this 2x times x plus 1 to the 1/2, it'll go over. This 2 and that 2 will give us a 4x, and x to the 1/2 times x to the 1/2 is just a x plus 1. I said that poorly, but this is what I meant. Minus an x squared, all divided by a 2 times x plus 1. If this is to the 1 and this is to the 1/2, we get to the 3/2. Let's distribute. This is equal to 4x squared plus 4x minus x squared, all divided by 2 times x plus 1 to the 3/2, which is 3x squared plus 4x all over 2 times x plus 1 to the 3/2, which for what we're going to do is convenient to factor out an x and say f prime of x is equal to x times 3x plus 4 all divided by 2 times x plus 1 to the 3/2. Perfect. We have found our derivative. I'm going to rewrite it on the back side. F prime of x is equal to x times 3x plus 4 divided by 2 times x plus 1 to the 3 halves. 2x plus 1 3 halves x 3x plus 4. Perfect. So why are we doing this? To figure out where we're increasing and decreasing. So note that x is always bigger than -1. So the only way to get a negative number out of our denominator is if x were to be less than 1. And in fact, we couldn't do that because we're going to cube it anyway. So that means what we care about. Let's figure out where we have our critical points at. Well, f prime of x is equal to 0 when our denominator can't be equal to 0. Either x is equal to 0 or x is equal to -4/3. But -4/3 is out of our domain, so we know that we have one critical point. We know that when x is equal to 0, that's where this function has a horizontal asymptote. And if you look to the left, when x is a negative number, this is negative times positive. So we know that f prime of x is less than 0 when x is less than 0, and f prime of x is bigger than 0 when x is bigger than 0. By our first derivative test, that implies if it is decreasing and then increasing, that x equals 0 is a local min. So this is really 5 and 6. We figured out where our intervals of decrease, our intervals of increase, and our local max and min if they exist. The last one is 7, is to take our second derivative. And I worked this one out over there. Just want to have my cheat sheet up. So f double prime of x, and this is another one that's going to be long, we'll finish that on another sheet of paper. F double prime of x, and I'm going to use 3x squared plus 4x divided by 2 times x plus 1 to the 3 halves. I'm just going to multiply that x back in, and I'm going to use the quotient rule on that thing. So this is going to be equal to our low, 2 times x plus 1 to the 3 halves, low times the derivative of the top, which is 6x plus 4, minus our top, times the derivative of the bottom, which is 2 times a 3 halves of an x plus 1 to the 1 half times the derivative of the inside, which is 1. All divided by our denominator squared. So I'm going to go through and just do some algebra first. We're going to move this 2 in with that 6x plus 4, call it a 12x plus 8 times x plus 1 to the 3 halves, minus, this 2 is going to cancel out with that 2, and this 3 is going to get grouped in here, minus 9x squared plus 12 times x plus 1 to the 1 half. Perfect. So denominator, all divided by 4 times x plus 1 cubed, because that exponent we squared 2, and we squared the square root of x plus 1 cubed. So we've got a x plus 1 to the 1 half here, we've got this fractional exponent over here. We're going to factor out an x plus 1 to the 1 half from the numerator. This is going to be equal to 12x plus 8 times what is going to be x plus 1 minus 9x squared plus 12 all times, oh, and I did it again, all times x plus 1 to the 1/2. I wonder how many of you guys noticed it. So, made a mistake with the first step. We did low times the derivative of the top minus the top. Right there. Minus the top times the derivative of the bottom. Funny thing, I made an error copying, not making my derivative. We'd get an x right there. When we distribute that 3 in, 3 times a 4x would give us a 12x, which would give us a 12x down here. Sorry about that. All divided by 4 times x plus 1 to the 5 halves times x plus 1 to the 1/2. We can break that x plus 1 cubed, x plus 1 to the 5 halves times x plus 1 to the 1/2. These will cancel, and we're left with 12x times x gives us a 12x squared. 12x times 1 gives us a plus 12x. 8 times x gives us a plus 8x. 8 times 1 gives us plus 8. And we're going to subtract 9x squared. And we're going to subtract 12x. And all that is going to be divided by 4 times x plus 1 to the 5 halves. Almost there. Almost. F double prime of x is equal to 12x squared take away 9x squared is a 3x squared. 12x take away 12x plus 8x is plus 8x. And then we have this plus 8 floating around. All divided by 4 times x plus 1 to the 5 halves. Perfect. So this is our second derivative. Now from our second derivative, we're trying to figure out if we have any inflection points, if we're concave up, or if we're concave down. And that boils down to the numerator. Our denominator is going to always be positive, so we need to figure out what our numerator is. Well, there's a couple different ways to go about it. The way I'm going to encourage you to look at it is, look, our numerator is a parabola. It opens up. And from the quadratic formula, they call this thing the discriminant. B squared minus 4ac is equal to b squared minus 4 times a times c, which is equal to negative 32. Since we can't take the square root of a negative number, we know this thing has no roots. Parabola opens up, no roots, always positive. So let me say that again. We wanted to figure out we wanted to figure out behavior of this function. Well, our denominator is never going, because of our domain restriction, our denominator will never be negative. So that means any sign change is going to come from our numerator. Focusing just on the numerator, we go, hey, that thing's a parabola. It opens up, and let's figure out if it has any zeros. Well, since it has no zeros, that means it looks something kind of like that. It opens up, it really looks like that. If it has no zeros and opens up, that means it's always going to be positive. So we know that f double prime of x is bigger than 0 for all x in domain. And we also know that there are no inflection points. So, putting all this in a graph, we know we're going through the point 0, 0, and let me find all my pages real quick. We know we have this vertical asymptote at x is equal to -1. And we know that we go up to positive infinity. What else do we know? We know that we go through 0, 0. We're not symmetric. We go off to positive infinity, so something like that over there. We have this asymptote. 5 and 6 are intervals of increase and decrease. We know that we are decreasing all through this area, and we're increasing throughout. We know we don't have any inflection points, so we know there's no way that we can go like this, where we go from concave up to concave down. We can, say, have a wiggle. We don't know enough to know, is this smooth and parabolic? Is it wiggling? After all, this is just a sketch. Concave up everywhere, no inflection points, vertical asymptote, horizontal asymptote goes to infinity. We're not symmetric. Our x-intercept is our y-intercept. So this is the sketch for example 2. So for example 3, let's sketch y is equal to x e to the x. So the first thing is our domain. Our domain for x e to the x is going to be all real numbers. 2, for symmetry, f of negative x is equal to negative x over e to the x. Negative f of x is equal to negative x e to the x. And just f of x is x e to the x. None of these three match each other, so we have no symmetry. That was 3. I always skip over intercepts, so we'll go back, call you 3. We'll do 2. For x-intercept, that's where y is equal to 0. 0 is equal to x e to the x. That implies x equals 0, and we'll cross at 0, 0. For a y-intercept, that's where x is equal to 0, and y is equal to 0 times e to the 0, which is 0. And our y-intercept is our x-intercept for this problem. 4, we got to talk about asymptotes. So, we're defined for all real numbers, so for asymptotes we're really just looking for x in the positive and x in the negative direction. So the limit, as x goes off to infinity, of x e to the x turns into infinity times infinity, which diverges to infinity. The limit as x goes to negative infinity is a little more tricky. Limit as x goes off to negative infinity of x e to the x, well, that's really the same thing as the limit as x goes off to positive infinity of negative x divided by e to the x, which would give us an infinity, a negative infinity divided by an infinity, which is one of our indeterminate forms. So this is equal to, by L'Hopital's rule, the limit as x goes off to infinity of -1 over e to the x, which goes to 0. So, as we go off to negative infinity, the limit as x goes to negative infinity of x e to the x is equal to 0. Perfect. So we've got domain, we've done intercepts, we've done symmetry, we've talked about asymptotes. Now we need to start with our derivatives. So, if we know that y is equal to x e to the x, then we know that y prime, and I'll call it f prime of x, is equal to the derivative of our first times our second plus our first times the derivative of our second. which for argument's sake I'm going to call e to the x times 1 plus x. So looking here, e to the x is always some positive number. Could be really small, but it's always going to be positive. F prime of x is less than 0 when x is less than negative 1. F prime of x is bigger than 0 when x is bigger than, negative 1. And f prime of x equals 0 when x equals negative 1. So since we are decreasing when we are less, since we are decreasing and then we are increasing, this tells me that we have a local minimum. And we're going to go through the point f negative 1, which is negative 1 e to the negative 1, which is negative 1 over e, which is like negative 1 over 2.7. I'd plug this into a calculator and have it give you a nice decimal. So that is our intervals of increase, our intervals of decrease, our local max or local min. Now we have concavity and inflection points. So if f prime of x is equal to e to the x plus x e to the x, f double prime of x is equal to e to the x plus derivative of our first times our second plus our first times derivative of our second, 2e to the x's plus an xe to the x, which for the sake of argument is going to be equal to e to the x times 2 plus x. So we know that we are concave down when x is less than 2, and we are concave up when x is bigger than 2, and we have inflection point when x is equal to negative 2. I did that whole thing too fast. I'm sorry. Our second derivative is negative when x is less than negative 2. Our second derivative is positive when x is bigger than 0. That is a true statement, but it's equally true to say when x is bigger than negative 2. And it is definitely true that we have an inflection point when x is equal to negative 2. The y-coordinate for that point, negative 2 over e squared. So this was a fairly quick one. Let's get to graphing this thing. So we know we have this horizontal asymptote where we are defined for all real numbers. We're going to go through the point 0, 0. As we go off to positive infinity, as x increases to positive infinity, well, that means we're going to go off over here. Since we know that x has to cross at this point, it's continuous everywhere, and limits to 0, that means I know we have to look something like this. That takes care, I'm looking off camera, you guys can't see exactly what I see. So we went off to positive infinity, and we went off to 0. 4 was talking about asymptotes. 5 was talking about increase and decreasing. So we know that we're going to decrease to negative 1, and then we're going to start to increase. So we're going to decrease till negative 1, and then we're going to start to increase. And we have this inflection point here at negative 2. So this is kind of my sketch of what y is equal to x e to the x looks like. So we're really, like I said, don't think of it as you have to hit every step in the process. Think of it as an overall sort of idea. Think of it as a big picture. Think of it as a guide. That you have to work with your original function, you have to work with your derivative, and you have to work with your second derivative. So the last thing we're going to do is we're actually going to talk about a special kind of asymptote, a slant asymptote. We can have functions so far that limit to, say, either positive infinity, they can limit to negative infinity, or they limit to some number, say 0, or positive a half, or whatever that actually is. But some functions are going to diverge to positive infinity or negative infinity in a predictable way. Some functions have what they call a slant asymptote. Some people also call them oblique asymptotes. What it is it's an asymptote that follows the equation of some line. So, how are we going to find a slant asymptote? We're actually going to use polynomial long division. So, an example with the slant asymptote, and my battery's been giving me issues, so I have worked this example out and I will talk you guys through it. So for our final example, we have this polynomial function, or this rational function, if you will. And the thing to notice is that the degree of the numerator is exactly 1 greater than the degree of the denominator. The degree of the numerator is 3, and the degree of the denominator is 2. When the degree of the numerator is exactly 1 than the degree of the denominator, you know you're going to have a slant asymptote. But let's continue. We've developed this 7-step process, so let's work our way through it. First off, the domain. So we have a rational function. The domain of rational functions is all real numbers except for where the denominator equals 0. Well, this denominator, x squared plus 1, never equals 0. There isn't a real number you can plug into it that'll make the denominator equal 0, so that means we can plug any real number into this function. So we know that our domain is all real numbers. Next, intercepts. To find our intercepts, you pick one and you start with it. I always start with x-intercept. The x-intercept is when y is equal to 0. And I have this notation written a couple times. I don't know if I've explicitly said it, but this kind of equal sign arrow is the word implies. So x-intercept implies that y is equal to 0. So we took y and we set it equal to 0. When we solved for x, we got x is equal to 0. It has an odd multiplicity, so we know that the graph of this function crosses the x-axis at 0, 0. Similar for the y-intercept. For the y-intercept, we let x be equal to 0. Well, when x is equal to 0, y is equal to 0. But we knew at this point what our y-intercept was. They happen to be the same point in this equation. So, moving on, after we find our intercepts, now we test for symmetry. To test for symmetry, you need 3 things. You need an f of x, you need an f of a negative x, and you need a negative f of x. Once you have all 3 of these things, it's a compare. You compare f of x with negative f of x. If they're equal, it's even. In this case, f of x and f of negative x, they weren't the same function. So we know that f of x is not even. But f of negative x and negative f of x, they're the same function. So that implies this thing is odd. So for symmetry, f of x, f of negative x, negative f of x, and compare. So, F4. Part 4. Asymptotes. So, like I said, notice how the degree of the numerator is exactly 1 more than the degree of the denominator. That tells us that f of x has a slant asymptote. And so what we do is we're going to use polynomial long division and our goal is to have f of x turn into f of x is equal to mx plus b plus some g of x over x squared plus 1. This is going to be our goal. This denominator is going to be right here, and we want to use polynomial long division to get an equation of a line plus some remainder term. So we do that right here. We figured out how many times x cubed goes into x squared. So in using polynomial long division, we want to figure out how many times x squared plus 1 goes into x cubed. And we go, well, I know I have to multiply an x squared by an x to get an x cubed. So when we do that, we multiply x by x squared to get an x cubed, and an x by 1 to get an x. We go through and we subtract this entire quantity. X cubed take away x cubed is 0, and then 0 take away x is a negative x. This down here turns into our remainder. And we have shown that x cubed divided by x squared plus 1 is equal to x minus x divided by x squared plus 1. Perfect. So this is of the form mx plus b. Just for this problem, m happened to equal 1 and b happened to equal 0. Won't always work that way, but we do have f of x is equal to some mx plus b minus a remainder term. Plus or minus remainder. And now think about what happens with limits. As x gets really large, x divided by x squared plus 1, this thing limits to 0. So as x gets larger and larger, the amount that this contributes to y becomes negligible. And this says, as x gets incredibly large, our equation is going to look like the equation y is equal to x. And like I said, as x gets big. So we have our slant asymptote. We have it in the negative direction too. If the limit as x goes to positive infinity is going to go off to positive infinity, and the limit as x goes off to negative infinity is going to go down to negative infinity. We have vertical asymptotes where our denominator equals 0, but there's no way for our denominator to equal 0. So we know we only have one slant asymptote. Along the line y is equal to x. Perfect. So now that we have our slant asymptote, we move on to 5. For 5, we need intervals of increase or decrease. I used the quotient rule. Be careful with some algebra. And we get down here. I prefer to factor my first derivative. I prefer to factor all my derivatives to kind of see their parts. So when we take a look at this, x squared is always greater than or equal to 0. X squared plus 3 is always greater than 0. And x squared plus 1 squared is always greater than 0. What this tells us is the derivative is always greater than or equal to 0. And the only time it equals 0 is when x is equal to 0. So we get f prime of x is positive, is increasing for all x different than 0, and we are horizontal when x is equal to 0. That means f of x is increasing on this interval and is horizontal at that point. F of x is never decreasing. For our local max and local min, you either have to increase and decrease from a point, or you have to decrease and increase from a point for there to be a local max and a local min. What we have is we increase to a point and then increase from it. If we were dealing with this in higher dimensions, we'd call that a saddle point. But this is neither a local max nor a local min by that first derivative test. So 7 is about concavity, and I'll give you a warning that this derivative is kind of tricky. I forgot to put a squared there when I was working it out, and it took me longer than I would like to admit. But going slowly with the quotient rule, we are able to reduce our first derivative down to this thing. I lied. Down to this thing. And I do want to show you the trick. This is just applying the quotient rule. And I believe the book skips from this step to this step. Once you apply the quotient rule, we're going to gather some like terms and get here. X squared plus 1 squared times 4x cubed plus 6x minus the x to the 4th plus 3x squared times 4x times x squared plus 1. all divided by x squared plus 1 to the 4th. Notice how we've got an x squared plus 1 here, we got an x squared plus 1 here, and we got 4 of them down here. So I'm going to grab one of these x squared plus 1s in the numerator, factor it out, and that's where this thing comes from. X squared plus 1 has been factored out of our numerator, and I use it to cancel off with 1 in the denominator, which is where we're getting this cubed in the denominator from. At this point I didn't need the square brackets anymore, so I chose not to write them. And we use the distributive property to get from this line to this line, and going from here to here is just algebra, and from here to here I factored out a negative 2x. The book leaves the negative 2 in, I think, and just pulls out an x. Potato, potato, however you want to do it. But once we get here, the thing to realize is that our second derivative equals 0, or we have an inflection point when x is equal to 0, or when x is equal to plus or minus the square root of 3. So we have these 3 inflection points. When x is equal to 0, and the y-coordinate that goes with it, when x is equal to the square root of 3, and the y-coordinate that goes with it, and when x is equal to the negative square root of 3, and the y-coordinate that goes with it. These are just our inflection points. We also have to figure out when we're concave up or concave down. We know concavity changes when x is equal to 0, or when x is equal to plus or minus the square root of 3. So we make a table that have 0 and plus or minus the square root of 3 on it, and we come up with 4 test regions. We need a test on either side of these points. I rewrote our second derivative, and I factored the numerator, and I put the first term right here, I put the second term right here, I put the third term right here, and the denominator down here. And now I picked a number. I had to pick a number less than the square root of 3. I didn't want to get, less than the negative square root of 3. I didn't want to get out a calculator and figure out what it is. It's somewhere in between negative 2 and negative 1. So I, at random, picked negative 5. Could have picked negative 500. I just needed something less than the negative square root of 3. So negative 5 times negative 2 is a positive number. Negative 5 plus the square root of 3 is a negative number. Negative 5 minus the square root of 3 is a negative number. And negative 5 squared plus 1 cubed is going to be positive. Notice that this thing is always going to be positive, the denominator. Now when we have a positive times a negative times a negative times a positive, all of those signs would wind up being positive, which means we're concave up. Then we have to go in this test region between the negative square root of 3 and 0. I chose negative 1. Negative 1 times negative 2 is positive. Negative 1 plus the square root of 3 is positive. Negative 1 minus the square root of 3 is negative, and the denominator is always positive. Positive times negative divided by positive is negative, which means we're concave down. 2 more test regions. I chose positive 1. We get negative, positive. Multiply all that together to get a positive, and I chose positive 5 for the sake of symmetry. Negative, positive gives us a negative. The intervals that were where we're positive were concave up from negative infinity all the way to negative square root of 3, along with on the interval from 0 to the square root of 3. And then concave down everywhere else. Negative square root of 3 to 0, and then from square root of 3 off to positive infinity. At this point, we have everything we need to sketch a curve. We're horizontal through the origin, and this dashed line, the equation of this dashed line is y is equal to x. So we are concave up until we hit the square root of 3, then we're concave down and we approach that line. Similarly, we are horizontal, concave down, and then we switch to concave up at the negative square root of 3. The big takeaway from this one, and I'm sorry I had to go fast, is these slant asymptotes. Your trick, your clue, the thing that lets you know is that the degree of your numerator, and this is important, there we go, the degree of your numerator is exactly 1 higher than the degree of your denominator. So for instance, if we had f of x equals 3x to the 4th minus x squared plus 2, divided by x cubed minus x plus 1, this function has a slant asymptote. We know that because the degree of the numerator is greater than the degree of the denominator. Perfect. We would then have to use polynomial long division. We'd have to figure out x cubed minus x plus 1 and 3x to the fourth minus x squared plus 2. So, and we would have to ask ourselves, we'd go, well, what do I have to multiply x cubed by to turn it into a 3x to the fourth? And you go, well, I need a 3x. 3x times x to the cubed is 3x to the fourth. 3x times negative x is a negative 3x squared. And 3x times 1 is equal to a positive 3x. A little reminder about polynomial long division is use your placeholders. I am going to go through and I'm going to rewrite this as plus 0x plus 2. So we have a column of x to the fourth, a column of x squared, and a column of x's. When we go through and subtract 3x to the fourth, take away 3x to the fourth is 0x to the fourth. Negative x squared, take away a negative 3x squared is x squared plus 3x squared. I said all of that poorly, but it's going to be plus 2x squared. And 0x take away 3x gives us a negative 3x. And then we're going to add 2 to it. Perfect. So then we would have to ask ourselves, then we would have to ask ourselves, well, what would we have to multiply x cubed by in order to make it a 3x squared? And we go, well, we can't. So we know that our slant asymptote, or I should say that this thing is equal to 3x, and then we're going to add 2x squared minus 3x plus 2 divided by x cubed minus x plus 1. So we know that this equation is going to have a slant asymptote along the line 3x. Because after all, this is going to contribute less and less and less as x gets large. The only thing that's going to contribute really is this 3x. Same thing in the negative direction. We don't need a limit. We don't need to use a limit to prove that this is going to be a slant asymptote by making the observation that the degree of the numerator is 1 greater than the degree of the denominator. That's all you need. We use polynomial long division to figure out what it is, but that's it. Also, once you figure out what your slant asymptote is, you never need to revisit this thing. You make the observation, you get the information you need, and then you put that away. You never go back and work with this form. You only put it in this form to figure out what your slant asymptote is, and then go back to working with this thing. For homework, go off and do these, and it took some time to figure it out. Do 1, 13, and 21. 61 through 67 odd. There's going to be 5 curve sketching, and they take some time, and there's going to be 2 just find slant asymptote. And for slant asymptote, you use polynomial, poly-long division. All this will be due on Friday. I want to look at a calendar before I tell you what day Friday is, but this assignment will be due on Friday. This was 4.5. Like I said last week, we're going to skip 4.6, so next video will be on 4.7. Take it easy, you guys, and I will talk to you next time.